Good. All right, we're going to go ahead and finish up security. I'm glad we went through all that last class because this is getting kind of long. So you remember last time we talked about security from an operating standpoint, which, let's see, what are we talking about? A lot of protection mechanisms. We used an access 2D array in order to
2D list
to store all the permissions for the domain and the file, or the user in the file. Is when we do protection. We're on the security end, which we're talking about different characteristics. You recall the three most important things: confidentiality, integrity, and availability. And basically the tool we constantly use in order to support those, or at least the first two, is called encryption. And then we need to come up with a way in order to make everything still available. So we talked about a few encryption schemes, but now we're going to start talking about authentications. And this is when the user logs in, like just now earlier today. It asks for my username. I put in root. That's identification because I'm identifying myself as root. But then it asks for me to authenticate myself through a password in order to ensure I am who I say I am. And so that's what authentication is. Right here, they're calling it in the book, constraining a set of potential senders of a message. All right. Complementary or sometimes redundant to encryption? Sure. Usually, well, wow, this is going really in depth. You can have a set of key messages authenticators, so you want to have some function generated authenticators for messages. Okay, great. Yeah, you just don't want that function to be reversible. So they're assuming that we're doing network authentication, and that's why this is so verbose. Is it presenting it this way? For a message M, a computer can generate authentication A such that it can only compute V if it possesses S sub K. So if we go back to V sub K, let's see. That's the way to verify it. So it can only verify it if it knows the secret. So holding the secret can generate the authenticators. Computers not holding the secret cannot create the generators. Basically, authenticators are generally exposed. They set to network. It must be feasible to derive SK from the authenticators. Okay. All right. Basically, what this whole slide is trying to say, in a kind of in a very cumbersome manner, I'm going to say, is that when you want to authenticate something, you need to make sure that when a user sends its authentication, that no one else can copy it. Or furthermore, that no one else can forge it if they don't have the right information. So there's two problems here on the network. One is a user forging the authentication somehow, and the second is people eavesdropping and finding out someone else's authentication information. So to help with some of this, this is going to help with the attacker not being able to, hold on, preventing the attacker from being able to forge any type of information or be able to gather any information is what they're going to use with hash functions. Okay. The idea is that if, let's say you're sending a message, let's say Alice is sending to Bob, and Bob wants to make sure that Alice, the message he got, is actually from Alice. So Alice is going to attach something to it, maybe a message digest or a hash value that is the hash of the entire message. That way, if the message is changed, then what Bob's going to do then is take the message, compute the hash, and then if the hash doesn't match Alice's hash, then he's going to say something's been tampered with. All right. So for a moment here, ignore the fact that the attacker could recompute the hash. Let's just assume that the hash is secured, sent on a secure channel, but the message is not. Just to further the security along, we'll fix that error in a moment. But the idea is that once you have the message digest, you can confirm that the message sent has been tampered with because you recompute the hash and match it with the other one. The attacker, of course, needs to make sure that he can't somehow come up with a separate message that still has the same hash. And so you need to make sure that your hash function is complex enough so that attacker just can't initially reverse it. Do you understand what I'm saying, or is this
Yeah.
overly complicated?
Yeah.
Second one, or both?
Yeah, your hash function probably should just be like something mod too.
Right, okay. Yeah, we could probably fix that pretty fast. Common message digest functions are MD5, which is now completely broken. So don't use MD5 or any of its predecessors like MD4. SHA-1 is considered, I forgot the term they used. They consider it somewhat mainly secure right now, but should be broken soon, is what they're saying. Last I checked. So you should.
That's encouraging.
It's China's been attacking SHA-1 a lot, which makes sense because NSA used it for a long time. So use SHA-2 instead. But the idea is that MD5 has a 128-bit hash, so it's just not mod 2. It's actually creating a lot of different bits. And then SHA-1 has 160-bit. Again, could be considered, usually more bits equals stronger, usually. But that's only a piece of the equation. SHA-2 actually has a variable number.
Why 160? Because that just seems like an odd number.
All right. So what's going on with these encryption schemes or hash schemes is they're going to be used a lot, over and over again. So they want to optimize it on performance. So they want to make sure that this bit is as small as possible for performance reasons, because it's a performance trade-off. I mean, yes, to us it sounds like 128 bits is nothing, but when you're doing lots of computations in order to produce a final 120-bit number, the higher the bit is, the more complicated things, or the more processing power it takes, and also the amount of storage increases as well. You have to realize that if it was just 160 bits just once for everything, that'd be fine, but it's usually 160 bits for everything. So you want to, the reason for 160, I know it doesn't make too much sense. That's just the sweet spot that they found. They ran a bunch of numbers, and this is what they came up with. Also, if you take, I think, 128 and you add 32 to it, you get 160. So then it's probably they're doing some form of 32-bit blocks inside their hashing. SHA-2 goes up to 512, although I think it goes as low as 228 or 256. It's been a little while. I'd have to go back and check. Okay. I'm skipping this.
Sweet.
Good.
Max don't exist.
Max don't exist. I'm done with Max. All right, digital signatures. Okay, this one actually you're going to encounter a lot. Huh? A lot. So I guess we should at least cover this one. What? Did you ever see this in the military?
A lot.
Never, right?
A lot.
Attached to everything. Okay. Digital signatures. So this is an asymmetric key. So we're going back to our public-private key infrastructure, and it's a way for a user to sign a message to make sure that that the message actually came from someone. So in a digital signature algorithm, computation is feasible to derive the secret key from the verification. Right. V is one way. Okay, sure. The key V is public and key S is private. Sure, S means secret. So if we go back into, oh, you've got to be kidding me. I didn't go through RSA. Thanks. All right. I'm going to wave my hands a little here, just to keep life a little simple. But digital signatures, remember, we're going back to the hash. With the hash, you can create the hash of the of the entire message. Then what you can do is the person who's sending it, he will encrypt that hash with this private key. Therefore, when you decrypt that hash, only people with the public key can decrypt it, but people with the public key cannot re-encrypt it with a new hash. Does that make sense? Because they don't have the private key. Therefore, if you send that digital signature out with other users, and it has the hash, you now can decrypt it, get the hash, and then run the hash on the message and see if it's been tampered with, any. And an attacker can't change the hash because he doesn't have the private key. Does that make sense? And usually there's going to be some type of salt or whatnot inside the digital signature to prove that, hey, look, they didn't just redo the
Salt.
Sounds delicious.
Salt. Have we not talked about salting?
No.
All right, so 1 moment. I'll just say there's an extra piece of information to show that, hey, look, this actually did come from the user. So it's a digital signature because since they have the private key, you know that it could only have come from them because when you decrypt it with your public key, you actually got the private key back, the salt or the name inside of the message. All right, salting. Before I go on, why are we using authentication as a subset? Why are we using digital signatures? This is the term they call non-repudiation, which is a funny term because, let's see, repudiation was it trying to not take blame for something, and then non-repudiation would be not taking the not of the blame. So it'd be taking the. Anyways, this term, it kind of is nonsensical to me. But all they're trying to say is that a person cannot refuse to accept what has happened. AKA, you're basically just providing proof that he did what he did, and they can't deny it. Was that confusing enough?
A recipient cannot deny that they received a message.
A recipient or the sender cannot deny that they sent the message.
That.
Because even you have the digital signature, right? They signed off on it digitally. All right, salting, which will be in your homework, so I'm glad we talked about it. All right. Did we talk about rainbow tables?
No.
Oh, rainbow. Oh, we didn't talk about rainbow tables.
They sound fine.
Oh, they're great. Okay. That's right. I'm getting my little camera out.
What's your compile thingy at right now?
Oh, probably long.
What letter of the alphabet?
It doesn't matter because it's going to skip around a lot.
Oh.
All right, but we'll find out just for you.
Frozen.
We're on crypto. We just got rid of AlgBoss. Oh, there's MD5 and SHA-1 generic, SHA-256.
I
Yeah.
wonder if I passed you.
No,
But you said it skips around.
it skips around a lot.
But I've got a 20-core processor.
I know that you are lying.
Am I?
Yes.
You never
On a
know.
laptop.
It's remote.
It's a remote
Yeah,
laptop.
Yeah.
All right, salting. Let's see if we can get some salt going on here.
He's taken over a few other computers. He's sending the data out to be processed.
I know that's what he said. I don't blame him. Any other good questions? All
My
right.
laptop over here is helping him compile it.
I bought 5 minutes on a supercomputer.
There are better uses for that money. All right. Okay. If we were going to MD5, the amazing password 1234, which of course is the password we are all using. Let's see if I
Not
can.
the password in front of it.
Yeah, that's my bank pin. not the
Okay, that's your bank pin. All right. Well, hang on.
Gotta throw numbers in there and a capital and a special character.
I don't have MD5. How about MD5 sum?
Five, so.
All right, so let's MD5 sum. Oh, it has to be of a file. MD5 sum. Let's see what we got. File. Can we just do it from standard in? Read in text mode. Ignore. Quiet. What if you do MD5?
Well, I just created a file that just has 1, 2, 3, 4 in it.
Okay,
So
that sounds great.
after we're compiling the thing, we don't need the Wi-Fi anymore, right?
I know you'll still need it. So we have 1, 2, 3, 4. What's the other one? Password.txt.
I guess.
Password. Any other amazing passwords we use in life?
Password.
I got that.
We just did that.
Oh shoot.
Yeah, I don't think we have any others, do we?
Password backwards.
A B C D.
Oh
No,
my
that's too
goodness.
advanced.
Oh, no, you need the one that has all the things, so it's
Oh, P,
capital P,
okay, hold on.
sign.
Hold on. I'm going to call it complex. P, $, lowercase w, 0, RD.
I feel like, yeah, I guess that works.
We'll go with that one?
Yeah,
That's what I have to do.
All right.
unless it needs two numbers.
So if I do an MD5 sum on 1, 2, 3, 4, I get that. Now, hold on a second. If I do MD5 again, it's still that. So I'm just going to call it, what is it, E7, DF7,
Can you convert that to
What?
decimal?
Why?
Yeah, that's gotta be in like binary. You can't just have the password.
What's wrong with hex? It's in hex.
No, that's not cool either.
Yeah, but we don't understand hex. We need that decimal.
Yeah, that's like way too many digits for me.
2, 8, 6, 7, 5, 5, F, dot, 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 and this is for password. And I don't know why I'm making this complicated, because it's actually a really simple explanation of why we do this. And then what was the other one? P at $, $W0 RD. Okay. Nine nine five four. All right. 9954182. Okay. So, if every system in the world used MD5, and you got to hold the password file, which is only holding the hashes, because the password just stores the hashes. Because the way it works is that once you have your once you put in your password, it computes the hash, stores the hash. That way, when you give it its password, it recomputes the hash based on what you gave it, and then compares that against the hash file. The point of that is, hopefully, there's no way. I'm sorry, people at home. Hopefully, there's no way to go from the hash value back to what's being passed in. That's what they're explaining, and that's actually a decent. If your algorithm's good enough, that's actually pretty good. Even if I put in SHA-1, what I'm about ready to explain, or SHA-2, what I'm about ready to explain to you is a problem. So MD5 has 128 bits. So if that's 128 bits, how many different possible combinations are there?
A lot.
So that's 2 to the 128.
It's actually 3 lots.
But how big is this?
Big.
So what they do, and this is one thing to keep in mind. If everyone's using MD5 and you got to hold the password file and you saw E7DF7 dot 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 dot, what does that mean the password is?
1, 2, 3, 4.
Yeah, 1, 2, 3, 4. So what people did, no joke, is they would compute the vast majority of these, and they would compute all the hash. They would start randomly choosing passwords and then storing what the password is in here. So like, you see this number, you know to use this password. So you'd have what's called a rainbow table.
But 1, 2, 3, 4, 5 goes to something completely different.
Yes,
than
but you
that,
just
right?
store what it is. You
Yeah.
store your
No, I
rainbow
get that
table.
part. I'm just asking, like, if you put in 1, 2, 3, 4, 5, you get completely different set of
Right.
things,
So let's go
right?
back and do 1, 2, 3, 4, 5 just to show that this is actually somewhat good. D5, 7.
Okay, cool.
Yeah, it's completely different. Well, close enough. Okay. So there are called rainbow tables out there of what MD5 is of all these passwords. So how can we get around this? We have something called
The encryption.
encrypt encryption. Oh, that just kicks the can down the road. Encrypt encryption. What are you going to encrypt it with?
Just keep infinitely kicking.
Oh, I see what you're seeing. Yeah, so you would come up with a. Well, hold on. Explain to me.
MD5 sum, the MD5 sum of 1, 2, 3, 4.
Oh, so you just do MD5 on top of this, but then you just compute the rainbow table of MD5 of MD5.
But you have to know that how many lines down the road they're using.
Oh, okay, so you would have different machines use different number of MD5s.
Potentially.
Potentially, okay. So actually, it's not a bad solution. I like it. The only issue is that it starts to get computationally complex.
In fact, you're going to MD5 sum the number of times you're going to do it, and you're going to do it that many times. That might be a really big number.
That's gonna take forever.
Stop.
You put in your password. You're just like, hold on, bro.
So I opened up my kernel thing and it's on a black screen. Is that bad?
Oh, that's very bad. Oh no, it's still going.
Okay, cool.
You gotta push the key.
Oh,
Oh man, that would have been bad. All
I
right.
would have given up.
So what they did instead is every time your operating system installs itself, it creates a salt, which is just some random string. Maybe it's like A57 $, big B 0. And then when you ask for your password, it pins this either to the beginning or the end. So in other words, you're not MD5ing the password, you're actually MD5ing the password plus the salt. And what that means is it's going every system, assuming every system has a different salt, all the numbers coming out over here are going to be different values. And the only cost is adding a couple more values to the end of the password or to the
How do
beginning.
you know what your recipient's salt is?
When they tell you, they freely give out what their salt is. Every system will tell you what its salt is. So this is public knowledge. It's like the public key, so to speak. And that's perfectly fine, because the whole point of this is no one should go out and pre-compute these numbers. You can't. The reason why this was a problem is someone could sit down and spend 3, 4, 5 months and try and generate the entire rainbow table for something, and actually purchase the storage for all of it, which is extensively very expensive as well. Now it's not feasible to do that anymore because that's only going to work on one system, and you don't even know which system that's going to be when it comes out. Because another thing that'll happen is they'll try and change their salts. When they ask for a new password, they may change the salt as well.
There's still only so many possibilities, though.
Right.
Yeah. But so once they compute that whole table, though, all they have to do is send it a.
Yeah, find out what it is. Yeah. The problem is computing this table is going to take an extremely long time. But if you only had to do it once, you could use a supercomputer, massive storage, compute the silly table, and then you'd be able to break into a whole slew of systems. Now, if you actually spent the time to do that, you could only break into one system.
All right, now with pepper. It's a legit question. I've seen it.
Really?
Yes, there's now salt and pepper, I guess.
Wow, I guess you're going to a
Okay.
second one or something? I don't know. I honestly don't know.
I'm Googling salt and pepper hashing. It's just giving me reps.
Whenever you say salt and pepper, I can only think of the song. Push it.
Oh, it is a thing. It's a secret add.
As I was going through storing my PHP password, they had a salt and pepper.
Wow.
A pepper is not stored alongside the hashed out function.
Oh, so it's a secret internal. Whoa.
A pepper is a secret added to an input, such as a password prior to being hashed, with a cryptographic hash function.
Oh, that makes sense. Because they're going with the whole white-black thing. Because salt, no, that doesn't make sense. No, that makes sense, because it's white box, so it's showing you what it is. And then pepper's like black box, where you can't see it. That makes sense.
How would you read a rainbow table?
Oh, it's just a giant table of these hashes, of these strings, and you just index into it, and that's your password to get.
And it's got like the password next to it, or you don't even need that.
You don't really even need
You
that.
see what the hash is, you tell it the hash, it gives you the password.
Think of it as a hash map, but your key is this. It's mapping to
And then
password.
it gives you the password, and then you can log in as that.
Yes, or it gives you a password that produces this hash.
Right.
Because there are multiple passwords that are going to go to a hash. All right. Now, that was great. Any other questions? Good.